Welcome to Module 10. In this video, we dive deep into computer vision, exploring how we can teach machines to see and interpret the visual world. In the previous module, you built your first machine learning model. Now, we take that knowledge and apply it to one of AI's most striking fields: how machines process images, pixel by pixel. Let's begin with part 1, where we address why images are uniquely challenging for computers to understand compared to standard data types. While you see a photograph, a computer sees a grid of numbers. Grayscale images are 2D grids of brightness values, while color images are 3 such grids stacked together. Consider this 5x5 grid. A computer identifies an edge by detecting a rapid, sharp change in brightness values from one cell to the next. Why not just flatten the grid and use a standard network? Doing so creates a massive number of weights, making the model inefficient and hard to train. Furthermore, flattening discards spatial structure. A cat's ear in one corner would be treated entirely differently than the same ear in another spot, forcing the model to relearn patterns at every position. To solve this, we need parameter sharing and locality. This brings us to the Convolutional Neural Network, or CNN, which is designed to process spatial data effectively. Now for part 2, the convolution operation. This is the core mechanical trick that makes modern computer vision possible. The foundation is the filter, or kernel. It's a small grid of learned weights that acts as a pattern detector, scanning the image for specific features like edges or textures. The operation is simple. The filter slides across the image. At each stop, we multiply the filter weights by the underlying pixel values and sum them to produce one output value. The sliding process is controlled by stride and padding. Stride determines the step size, while padding manages how we handle the edges of the image grid. As the filter completes its slide, the results form a brand new grid called a feature map, which essentially acts as a map of where specific patterns appeared in the image. Real networks use many filters at once, each creating its own feature map. These are stacked into a volume, allowing the network to detect multiple complex patterns simultaneously. This convolution approach solves our initial problems. It keeps the number of parameters low through weight reuse and preserves spatial structure by sliding across the 2D layout. Moving on to part 3, we'll see how stacking these simple convolutions with a few more ingredients allows us to build a network that can genuinely recognize complex objects. By stacking several convolutional layers, a hierarchy emerges naturally. Early layers detect simple ingredients like edges and color blobs, while deeper layers combine these into textures and ultimately entire objects. After each convolution, we use an activation function, usually ReLU. It keeps positive values but sets negatives to 0, allowing the network to model nonlinear, complex patterns. Next is pooling, which shrinks feature maps. Max pooling, for example, takes a patch of values and keeps only the highest one, reducing data size while preserving the strongest signals. A full CNN pipeline repeats these convolution, activation, and pooling blocks. Each pass builds richer, more abstract features on a smaller grid, before flattening the final result for classification. Once the final pooling layer is done, the data is flattened into a single list of numbers. This list is passed to the fully connected layers we learned about in Module 6, which handle the final classification. For instance, a mini-architecture for handwritten digit recognition might start with a 28x28 image, shrink through convolution and pooling, and end with 10 output neurons representing each digit. Now we reach part 4, understanding how these networks learn, the history behind their success, and the practical shortcuts used today. Training a CNN uses the same backpropagation process as simpler networks. It compares predictions to labels and nudges the filter weights until it successfully detects edges, shapes, and finally objects. Unlike early computer vision, which relied on hand-designed rules, CNNs learn their own filters from data. This makes them more robust and capable of discovering patterns that humans might miss. The 2012 AlexNet breakthrough proved this power at scale, crushing previous methods in the ImageNet competition and sparking the current deep learning revolution. Architectures have evolved significantly since then, from LeNet in 1998 to deeper models like VGG and ResNet, which introduced tricks like skip connections to train ever deeper networks. Since training large networks is expensive, we often use transfer learning. We reuse the early layers of pre-trained models, which already detect general features, and retrain only the final classification layers. Finally, Part 5 looks at real-world applications of computer vision, from medical imaging to self-driving cars, and acknowledges where these systems currently face limitations. Today, CNNs are ubiquitous. They assist doctors by scanning medical imagery, help agricultural drones estimate crop yields, and ensure quality control on high-speed manufacturing lines. In medical imaging, CNNs are showing impressive results, matching dermatologists in classifying skin lesions and flagging tumors in radiology. However, they are best viewed as a tireless, expert second opinion, not a replacement for a doctor's final judgment. A critical limitation is data hunger and bias. Because a CNN only learns from the data it is shown, face recognition systems can fail on certain demographics if the training set lacks diversity. This is an intentional bias. It's a blind spot in the data. We also face the problem of adversarial examples. By changing just a few pixels in ways invisible to humans, researchers can fool a highly confident model. It proves CNNs are matching statistical patterns, not reasoning like we do. This reveals the honest picture. CNNs are incredibly effective at large-scale pattern matching, but they lack true vision. They possess no depth perception or common sense, a distinction that remains vital as their usage expands. Let's debunk some myths. First, a CNN does not see like a human. It only matches pixel patterns. Second, benchmark accuracy doesn't guarantee real-world success, as it often masks brittleness. And third, bigger models don't always mean better results due to diminishing returns. Time to check your understanding. Pause the video and consider these 4 questions. How do filters work? Why avoid flattening? What are common CNN limitations? And what is transfer learning? Your answers follow next. Here are the answers. A filter computes a dot product at each position. Flattening destroys spatial structure. Adversarial examples are a known limitation. Finally, transfer learning reuses pre-trained features to save time and resources. Keep this vocabulary list handy. Convolution, kernel, feature map, pooling, transfer learning, and adversarial examples. These terms are the building blocks of everything we've covered in this module. To recap, images are grids where spatial structure is key. CNNs preserve this using sliding filters. We stack these layers to recognize complex objects, though we must remain mindful of bias and the fact that these models lack true understanding. You've successfully taught a machine to see. In our next module, we move from visual patterns to the written word. Get ready to explore natural language processing. Congratulations on completing Module 10. You now have a solid understanding of how machines interpret images. I look forward to seeing you in Module 11.